Now it is your turn to write some code. In these labs you build and test this chapter's operations. In C there are 3 labs. One rule holds for all of them. Every program must free what it allocates. Each malloc gets exactly 1 free. This is Lab 1. Your goal is to build a full singly linked list in C, and then prove it works with a small driver program. Take your time. You have about 25 minutes. These are the functions you will write. Insertfront adds a new node at the start and returns the new head. Insertend adds a node at the tail and returns the head. List search looks for a key and returns a node pointer or null when the key is absent. Deletevalue removes the first match, frees it, and returns the head. Listprint shows the chain, and listFree releases every node. To test it, build the list 10, 20, 30, 40. Search for 30, which is there. Search for 99, which is not. Then delete 10, the head, and delete 30 from the middle. Print the list. You should see 2 values left, 20 and 40. A hint before you start. InsertFront returns the new head. So the caller must write head becomes insertFront of head, and K if you forget to save that return value, your list will not change. And end every run with list free, so each malloc meets exactly 1 free. Let's look at one solution. Try your own version first, then compare it with this one. We start with insertFront. InsertFront is the cheap edit. It calls malloc for 1 new node. If malloc fails, it returns the old head. Otherwise, it sets the data, and it points the new nodes next at the old first node. Then it returns the new node as the new head. 2 writes and no walking. If the list is not empty, we move a cursor with cur becomes cur arrow next until cur arrow next is null. That is the tail. Then we link the new node after the tail. The walk makes this big O of n. Next is insertend. This one is longer because it must walk to the tail first. Insertend makes a new node and sets its next to null because it will be the last node. If the list is empty, the new node is the whole list, so we return it. Otherwise it walks with prev and cur until cur holds the key. Then it relinks prev arrow next past cur, and only then frees cur. Always relink before you free. Last is deletevalue. It has 2 cases just like before. Deletevalue first checks the head. If the head holds the key, it moves head forward and frees the old head. The head has no node before it, so it is a separate branch. This is Lab 2. Here you reverse a list in place. That means you flip the direction of every next pointer without making any new nodes. This is the classic 3-pointer walk. Take about 30 minutes. Write a function called reverse that takes the head and returns the new head of the reversed list. You reuse the same nodes. Only the next fields change. To check it, reverse the list 10, 20, 30, and you should get 30, 20, 10. This is the hint. Keep 3 pointers. Prev starts at null. Cur starts at the head, and you need a save next. Each step does 3 things. First, save cur arrow next. Second, flip cur arrow next to point at prev. Third, move prev and cur forward. Before you run it, think about what breaks if you flip the link before you save the next. Let's look at one solution for reversing a list. Try your own version first, then compare. Here is the code. Prev starts at null and cur starts at the head. Inside the loop we do 4 things in order. Save the successor, flip this link backward, advance prev, and advance cur. When the loop ends, prev holds the old tail, which is the new head. Let's trace the first loop turn on 10, 20, 30. Change 1, save. We run next becomes cur arrow next. This is the most important line. We must save the successor before we flip anything, or we lose the rest of the list. Change to flip. We run cur arrow next becomes prev. Prev is null right now, so node 10's next becomes null. Node 10 now points backward. And notice node 20 is still safe because our save next still holds it. Change 3, advance prev. We run prev becomes cur, so prev now names node 10. Change 4, advance cur. We run cur becomes next, so cur now names node 20. The loop repeats the same 4 changes for 20 and 30. When it finishes, the list is 30, 20, 10. Time is big O of n, space is big O of 1, and no new nodes. This is Lab 3. Here you decide whether a list has a cycle. A cycle means some node's next points back to an earlier node, so there is no null at the end. The chain loops forever. This is a reasoning task. Take about 35 minutes. Write a function called hasCycle. It takes the head and returns 1 if a cycle exists, or 0 if it does not. Use Floyd's tortoise and hare. You keep a slow pointer that moves 1 hop each step and a fast pointer that moves 2 hops. If they ever land on the same node, there is a cycle. One warning about memory. A cyclic list must not be freed with a plain walk because the walk never reaches null. So in your test, build a cycle by pointing the tail at an earlier node. Detect it. Then break the cycle. Set tail arrow next to null before you free. Think about why the fast pointer is guaranteed to catch the slow one inside a loop. Let's look at one solution for detecting a cycle. Try your own version first, then compare. Here is Floyd's method. Slow and fast both start at the head. The loop runs while fast and fast arrow next are both not null, so it is safe to take 2 hops. Slow takes 1 hop, fast takes 2, and then we compare them. Let's trace it on a cyclic list, 1, 2, 3, 4, where 4 points back to 2. First, slow hops once. Slow moves from node 1 to node 2. Fast has not moved yet this turn, so it is still at node 1. Now fast takes its first of 2 hops. Fast moves from node 1 to node 2. We do not compare yet because fast still has 1 more hop to take. Fast takes its second hop. Fast moves from node 2 to node 3. That completes fast's 2 hops for this turn. Now we compare. Slow is at node 2, fast is at node 3. Are they the same node? No, so we loop again. Because fast gains 1 node on slow every turn inside the loop, the gap shrinks to 0, so they must eventually meet. Time is big O of n and space is big O of 1.